Hello and welcome to another paper review. So the paper we're going to look at is smooth approximation of mappings with rank of the derivative at most 1. I choose for this segment papers where the statement of the theorems are very easy to understand. Preferably they are understandable to someone who only knows calculus, for example, as is the case for this very paper. And in order to inspire you to read up more from their introductions and also to illustrate how the techniques, the abstract techniques of metric analysis and metric geometry can end up having concrete applications to classical questions. So this paper from 2022, published in Calculus of Variations and Partial Differential Equations, is from Pavel Goldstein and Piotr Hajwasz. Piotr Hajwasz was my former advisor, and his research and most of his papers are actually quite explicit in the problems that they deal with, and he's also well known for writing long, but on the other hand, clear papers. The introduction are usually very well written and with patience. He takes care of explaining the background, and he doesn't shy away from having a long paper that can paradoxically be in shorter amount of time. Anyway, the question the paper considers is a conjecture by Galeshki. I hope I'm pronouncing it the right way. Sorry, I didn't check that. Which says that if you start with a C1 function from some open subset of Euclidean space into the same dimensional space, so very simple, no big deal. So f is simply a once continuously differentiable function from an open domain into Rn, something you see in multivariable calculus. Furthermore, its derivative, which is an n by n matrix, satisfies the rank condition less than m. Of course, it's only interesting if m is strictly less than n, because of course every matrix n by n will have rank less than or equal to n. So you start with a function omega to Rn, and you assume that its rank is always less than m. Can f be uniformly approximated by a sequence of smooth mappings whose rank also remains bounded from above by m? So we want fi to uniformly converge to f. Maybe we will be happy enough if it did just locally. The point is that we have increased the regularity to say infinity, but also haven't allowed this rank to shoot up. The difficulty here is that the usual approximation technique, the go-to approximation technique to get C infinity functions are through mollifications. And this will utterly fail here because they are not at all respecting the rank condition. They notoriously can increase the rank. Okay, you can pause and think whether you would vote a yes or no for this conjecture, because I'm about to give you the answer. The answer is that in general, no. So they had a previous paper, this paper 7, that they reference a lot here. And from that paper, they quote two examples. There exists some C1 map from R5 to R5. Its rank is less than or equal to 3. but it cannot be, even locally, uniformly approximated by C2 mappings, which also preserve this rank. So even if we give up on C infinity approximation, you cannot even increase differentiability by one order while still retaining this. And similarly, there is a C1 map R7 to R7, rank less than 4, that cannot be approximated by C3 mappings. So here we go by 2 up with this. There is a lot of interesting links to many other objects. For example, homotopy groups of spheres, which is strange how they end up entering this story because, well, Euclidean spaces have null homotopies. And the source of these examples actually come from more general theorems, which they again cite here. So that's all negative answers. In general, this is not possible. What they prove in this paper, the main result of the paper, is that for the case of rank 1, indeed you can always approximate. So let's read the statement more carefully. Okay, and then there's one big condition, by the way, which is the restriction of being simply connected. I already mentioned homotopy, so this makes some sense, but also it doesn't feel like this is any genuine restriction, and there should be the claim should be true for many other domains as well, at least. Okay, so you start with a simply connected domain. You have a locally Lipschitz, so you can replace these by C1. That's actually how you first we've seen a lot of stuff in our area and query formulas about how Lipschitz maps are approximable by C1 maps. So we can, for simplicity, imagine these are C1. Okay, you have that, and you have this rank less than 1. Of course, you have to do almost everywhere because Lipschitz is differentiable only almost everywhere. If you had C1, then also this goes away because of continuity of rank. If it's true almost everywhere, it's true everywhere. Okay, then there does exist infinity smooth maps that approximate the function uniformly on compact sets and such that their rank is also never more than 1. So that is the positive answer to the conjecture in the case of rank 1. And the corollary is a local version of that. So a point of interest here is, okay, again, go back to this paper's introduction and read it. As I said, the introductions are written very well. Here's a summary of the idea of the proof. Now, I want to just read some important comment from here. Okay, so one method we use is they use is factorization through metric trees. Okay. Maybe it's in the abstract, that's why I missed it. Okay, so the statement of the theorem, as you saw, is understandable to anyone who knows calculus, multivariable calculus. But here's the point. The construction of this approximation employs techniques of analysis on metric spaces, including theory of metric trees, and basically a ton of stuff about Lipschitz functions, their metric differentiability, if you open up this factorization result. And it goes to show, this type of papers are a reminder of why we do metric geometry or metric analysis. Why just push the boundaries and generalize? The techniques, you never know where they will end up answering some questions that are then immediately relatable. So pure mathematics is not about just because we can generalize or for the sake of doing something. The tricks and the techniques that we develop sometimes, actually very often, help us answer classical questions. And number two, they also add new perspectives. So, for example, since 1990s, there has been a theory of Sobolev functions on metric measure spaces. And this is still a very hot topic and ongoing. It has helped us understand Sobolev functions in the Euclidean setting much deeper and much better than before. It has helped us see what is really essential to the definition and properties of Sobolev functions in Euclidean spaces. For example, it turns out that this foliation property of Euclidean space, that it's made up of a bunch of parallel hyperspaces or lines, is not truly significant for having Sobolev functions, which is very surprising because the very definition of Sobolev function through weak derivatives relies on this notion of partial derivatives. And what is partial derivative if you don't have axes, say? But again, that's another example to support this idea that abstract metric analysis is useful, other than being also beautiful, but that is a subjective thing. Thank you so much, and let me know if you want to see more paper reviews, what type of papers, and anything else that you like. And also please subscribe. Thank you so much.